So let me know if you can see the screen.
Yes, I can.
Okay, so this is where we had stopped last time. We looked at blocking assignment and non-blocking assignment and how it is different with respect to each other. And for excuse me, for design purpose, we have to use non-blocking assignments. We saw that because that is how hardware works. If you take a flip flop, there will be a delay of clock to Q, and the clock to Q delay will be modeled or simulated correctly using non-blocking assignments rather than blocking assignments. So wherever possible, we should use non-blocking assignments for our assignments to signals in Verilog. Any questions till this point?
No, no, not wrong.
Okay, so we'll continue with the next part, RTL modeling. So RTL modeling helps us design a system at a higher level of abstraction using Verilog language. We have seen that we can use procedural blocks to design concurrently in Verilog. Procedural blocks we have seen are of two types: initial block and always block. Initial block are used to model initial conditions or reset conditions. Always block are used to model combinational circuits, sequential circuits using flip-flops, etc. When you take an initial block or a always block, within the initial block or within the always block, it is all sequential execution, one after another, inside the initial block and inside the always block. But initial block, and let's assume that there are three always blocks: initial block, always block 1, always block 2, always block 3. In that case, inside the initial block and inside each always block, it is sequential execution. But logic of initial block versus logic of always block 1 versus logic of always block 2 versus logic of always block 3, it is all concurrent or parallel execution. So any logic of one block will work parallelly with respect to logic of other block. Across blocks, it is parallel execution. Within the block, it is sequential execution. We can use various assignment statements like we saw: blocking assignments, non-blocking assignments. We can declare registers, we can declare wires, we can declare integers. And there are some other statements like if then else, case statements, loops, etc. that we'll see. Each block in Verilog, when it has each statement rather in Verilog, when it has one more than one statement, has to have a begin and end to mark the start and end of that statement. Just like if you're using C language, you use a curly brace or a curly bracket for to create a group of statements. So similarly here we have begin and end as keywords. So this is in Verilog, everything is inside a module. So if you declare module something end module, so this is a module, okay, but there is nothing happening inside the module. Now this module has a input output ports declared. There are two inputs, there is one output, but still it is doing nothing because there is no logic declared inside it. So it's a module which is doing nothing for us. So but everything is inside a module. That is, this is to show you that everything is inside a module in Verilog. We are going to see some more examples of combinational circuits where in case of combinational circuits we know that outputs are dependent on current value of inputs, and based on that and the logic that you have, output, so input, current inputs and combinational logic will decide the output. So output is function of inputs. So what are some of the combinational circuits examples that we have seen? We have multiplexer, we have decoder, priority encoder, adder, etc. Now, if you take a two simple 2:1 mux, and we have to now this is a symbol or a block a block representation for it, and this is the simple 2:1 multiplexer implemented using basic gates: AND gate, OR gate, and NOT gate. So this is a structural level, netlist or structural level implementation of a 2:1 mux. Module mux2 underscore 1 out A, B and select. This is my port list. Out is a single bit output port. A, B, select, each of them is single bit input ports. I have a wire called SCL underscore A1 and B1 to connect the output of one gate to input of another gate. Then I'm going to instantiate these gates, not of I0. So not is the inverter. I give it a name label I0. Dot Y goes to select underscore. Dot A goes to select. So this is the correct way of doing the assignments. And this is the shortcut way of doing it. It is allowed, but you should not technically use it wherever possible. And two gates, two input AND gates are instantiated twice. First time it is called I1, second time it is called I2. In the first instance, input A is mapped to A1. Input A, okay, so that's the output. Output Y is mapped to A1. Then input is mapped to A, and the other input is mapped to select underscore. So that is how this particular signal mapping is done, port mapping is done. In the second instance, I2, the output is going to B1. One input is connected to B and the other input is connected to select. That's the second AND gate. And then we have the OR gate, which is called I3. The instance is given the label I3. Output is connected to final output. One input is connected to A1, the other is connected to B1. End module. So this is how you declare. This is how you do structural level modeling of a particular combinational circuits. Okay.
Okay, okay.
The same multiplexer can be designed using continuous assignments or behavioral modeling. So if you do it with a continuous assignment, module mux2 underscore 1, out A, B, select. This is my port list again. Out is single bit output, A, B, and select are input port single bit. It's a 2:1 mux. So I need one select line to select between two inputs. Assign. Now this is a continuous assignment outside the always block. Assign out is equal to A and not select or with B and select. So if you take this thing, out is equal to A ANDed with not of select, B ANDed with select, and then you or logically or you'll get the output. So this equation can be implemented using a continuous assign statement, which will again give me a 2:1 multiplexer. Now the same thing can be modeled using a behavioral statement or behavioral modeling method. Module mux2 underscore 1 out A B select is my port list again. Out is single bit output, A B and select are single bit input ports. There is a reg call out which is the same name as the output port. Why? Because I'm going to assign the value to reg out inside the always block. So according to Verilog guidelines and rules, if I'm going to assign to output inside the always block, I have to declare a reg with the same name. Then there is always block, always add A or B or select. These are my inputs and this is part of my sensitivity list or activation list. Any change in A or any change in B or any change in select line will trigger the always block. Begin the always block. If select equal to one tick B1, so this is called one tick B1 stands for one bit binary value. If select is equal, we are comparing. If select is equal to 1, one bit binary value 1, out gets B input, else out gets A input. These are non-blocking assignments. End always block end module. So here we are using a behavioral method for implementing a 2:1 multiplexer. Any questions on this?
No.
Similarly, we can implement a 4:1 multiplexer. Module mux4 underscore 1 out in 0 in 1 in 2 in 3 select. Now there is one single output, there are four inputs in 0 in 1 in 2 in 3 and there is a 2-bit select line. Why? Because n number of select lines for 2 raised to n number of inputs. That's how a multiplexer works. So there is a 2-bit select line. Now in this case again we can use a assign continuous assign statement. Assign out is equal to, this is called a conditional operator, question mark and colon. Assign out is equal to select equal to 2 tick b00 question mark in 0. So the way it is read is, if select is equal to binary value 00 in 0 goes to out. Else if select is 01, 2 tick binary value 01 in 1 goes to out. Else if select is 10 binary value in 2 goes to out. Else select is 11 in 3 will go to out. And in case of conditional operator statement, there should always be a default value. So else 0 is assigned to output. Since select is 2-bit binary value, it should be one of these four combinations, but there should always be a default value for conditional operators. So this is the conditional operator question mark and colon. So depending on the select line, one of the inputs is going to output. That is how a 4:1 multiplexer will work for you. End module. Yeah.
Yeah, that's fine.
So you can note down this example because this will be one of the examples where you'll write a test bench and simulate.
Yes, I took a picture of it, so I have it.
Right. So as you can see, a simple combination circuit or any digital circuit can be implemented using various methods. Structural modeling method, continuous assignment, which is also called data flow modeling, or it is clubbed with other modeling, or it could be pure behavioral modeling. It could be using continuous assignment and conditional operators. So there are various ways to implement a digital circuit. Any method is correct as long as it is following the Verilog and hardware design guidelines. There is any method that you use to design a digital circuit is correct. I was just talking about it. So we have one more method in this case. It's a behavioral modeling with a case statement. Again, we take a 4:1 mux. Out, in, and select is my port list. Out is single bit output port. In is a 4-bit input port. It's a vector 4-bit input port. Select is a 2-bit input port. Now there is a reg call out which is the same name as the output port. Why? Because this output will get assigned inside the always block. Always add select or in. So this is my sensitivity list. Any change in select or in, the always block is triggered. Begin the always block. Case select. So this select is a case variable. When select is 00, out gets in of 0. So 0th bit of in, because in is 4-bit vector. 0th bit of in goes to out. If select is 01, 2 tick B01, out gets in of 1. So the first bit of in value goes to output. If select is 10, out gets in of 2. If select is 11, out gets in of 3. For a case statement, there should be a default statement every time. So default value, in case none of this matches, out is equal to 1 tick binary 0. So out will be 0. End the case statement, end the always block, end module. Okay.
Okay, so what I didn't get is why in is part of the always block, because I thought only select is the one that changes.
Yeah, but if in changes, your output select remains same. Let's say select is 1 1, for example, and select remains 1 1 in that case. But select is 1 1, so that means out should get in of 3, the third bit, MSB bit. Now, if the third bit of input changes, it should get reflected in the change in output.
Oh, okay, I get it.
For that, input also has to be part of the always block activation list.
It's okay, I get it.
Okay. Now this is a decoder, 3:8 decoder. As if you can remember from the digital logic design, the decoder, the way decoder works is there are n number of inputs and 2 n number of outputs. Depending on the input value, one of the outputs will go high. Now, if you have three inputs, 2 3 outputs, that means 8 outputs. Depending on the input value, one of the 8 outputs will get activated. In this case, it is active low enable and active low output. Means one of the outputs will get deactivated. The rest of the outputs will be 1, one of the outputs will be 0. Active low enable. So there is an enable which is also active low. If it is 0, the circuit is enabled. If it is 1, the circuit is disabled. Let's look at the Verilog code for that. Module decoder. DC out enable bar. Now this is called as enable bar. Enable underscore is called enable bar. DC in. Enable bar will tell me it's an active low signal. DC out enable bar DC in. This is my port list. Out of which DC underscore out is the output port 8 bits. 7 down to 0 means it's a 8-bit output. Input enable bar single bit. Enable bar means active low input. Input DC underscore in is 2 down to 0 means it's a 3-bit input. 2 down to 0. There is a reg called DC out which is 8 bits because I'm going to assign it inside the always block. So the same name as the output, I have declared a register with the same name and the same width. Always at enable bar or DC in. This is my sensitivity list or activation list. Begin the always block. If enable bar means I'm checking if enable bar is equal to 1. If it is equal to 1 means it is active low. If it is 1 means it is not active. Not active means the circuit output can be disabled. The circuit output is also active low. Active low means all outputs are high. If enable bar is equal to 1, DC out gets 8 tick binary, 8-bit binary 1111 111. All outputs are deactivated right now. Else means if enable bar is low, means the circuit can be enabled. Begin the else block. Inside the else block there is a case statement. Case DC in. DC in is my case variable. DC in when it is 000, it's a 3-bit value. So when it is 000, output number 0 will go high. DC out is equal to 8 tick binary 1111 1110. When DC in is 000, the output number 0 will go high. When DC in is 001, output number 1 will go high. Rest of the outputs are deactivated. Since it is active low output, deactivated means 1, activated means 0. When DC in is 010, input value 3-bit binary 010, DC out will be this second output will go high, rest of the outputs will be deactivated. When it is 011, output number 3, all the way similarly up to MSB, which is 7. So if it is 111 DC in 7th output, 47 will go high. For a case statement, there should be a default. Default, all outputs are deactivated. DC out equal to 8 tick B 1111 1111 means all outputs are deactivated. End the case statement, end the else block, end the always block, and end module. So do you understand how this decoder is working? Have any questions?
No, it's fine. I get it.
So you can take a snapshot of this. If possible, you can write down. That is even better because that will help you practice a little bit. So,
Yeah, sure. I'll write it. I take a picture, then I'll write it when I'm studying it.
right, yeah, please practice because that's the only way you'll remember. Uh, Either typing or writing it out on a piece of paper. So that will help you to practice.
Yes.
Next is a priority encoder. So if you remember, a normal encoder is a reverse of decoder. In decoder, we just saw that there are n number of inputs and 2 raised to n number of outputs. So 3 inputs means 2 raised to 3 equal to 8 outputs. Encoder is reverse. 2 raised to n number of inputs, n number of outputs. So if I have 8 inputs, it is 2 raised to 3. Then 3 output, I will have only 3 output, n number of outputs. That's a normal encoder. In a normal encoder, if you take a 8 is to 3 encoder, only one of the inputs can be high at a time. We cannot have two inputs high at the same time. That's how a normal encoder works. But in real life, that's not how it will work every time. It is very likely that you will have more than one input high at a given time. So how do I resolve this in that case? You resolve this two or more inputs high at a time by using something called a priority logic or a priority encoder logic in this case. A priority encoder works obviously with priority. So if you have, let's say in this case, four inputs, we have to give priority to highest priority to one of the inputs. In this case, D3. If you see the truth table here, this is given to us and we have to write a Verilog code for this. So the truth table says if input D3 is high, I don't care about the other inputs. XXX means don't care. If D3 input is high, I will ignore the other inputs and outputs. Three outputs will be 111, X, Y, and V. If D3 input is 0 and D2 input is 1, I don't care about the other two inputs. Output will be 101, X, Y, and V. D3, D2 are 0, D1 is 1, I don't care about D0 input, output will be 0, 1, 1. If the upper three inputs are 0, D0 is 1, outputs will be 0, 0, 1. And all inputs are 0, I don't care about output. So all outputs can be 0 in that case. So I have to write a Verilog code for this because I have been given a truth table like this. So module priority encoder D0, D1, D2, D3, X, Y, and V. This is my port list. Out of which D0, D1, D2, and D3, each of them is an input port single bit. Output X, Y, and V are three outputs. So I can declare a reg here itself rather than declaring us on a separate line again reg X, Y, and V. Verilog as a language allows me to do this. Output and reg are declared in the same line, and X, Y, and V are individual outputs of single bit and registers also by the same name and single bit. Because I'm going to assign values to X, Y, and V inside the always block. In the always block, always at D0 or D1 or D2 or D3, these are my inputs. This is my sensitivity list. Begin the always block. As per the truth table, if D3 is equal to 1, equal to means I'm comparing if D3 is equal to 1, X, Y, and V concatenated. These are single bit outputs. If I concatenate them using the curly brackets is equal to 3 tick B111. So if D3 is high, I don't care about the other inputs. Outputs will be 111. X equal to 1, Y equal to 1, V equal to 1. I concatenate them and give a 3-bit value. Else if D3 is 0 and D2 is equal to 1, outputs will be 101. If D3 is 0, D2 1, outputs will be 101. X equal to 1, Y equal to 0, V equal to 1. Else if D1 is equal to 1, outputs will be 0, 1, 1. So it will follow this truth table. Else, since all inputs are 0, output will be 0, 0, 0. Don't care means we can have a 0 here in the outputs. 3 tick binary 0, 0, 0. End the always block end module. So we have written this Verilog code for a priority encoder truth table given to us. This is how priority encoders work. Any questions on this?
No, no question.
Okay. So next is the parity generator. Do you know what a parity is? If I give you 8-bit data, for example.
Yes, I know the parity bit.
So how do you define parity?
Well, it's just to check if it's even or the number of ones in the data. So if it's an even parity, then every time we check if the number of ones are even, and if not, we add one to make it even. Or if it's an odd parity, which is the most used case, then we count the number of ones in the data. And if the number of ones is odd, then we add a zero. But if the number of ones is even, then we add a one to make it odd. So it's like the last bit of we add one bit of to the data to check the parity, to make sure the parity is okay.
Right. So first we check whether it's an odd parity or a even parity. If I give a 8-bit number, and I have to check whether it's odd parity or even parity. Normally, as you said, normally we check for odd parity. That means we check for odd number of ones the given 8-bit data. If we have odd parity, then it depends what we want to achieve with that. Then that's a different story. But parity generator will give us that information whether it's a odd parity. Normally we check for odd parity, so we'll check here for odd parity. Module parity gen data and parity are my input ports, are my ports rather. Data is the input port 8 bits. Parity is a single bit output port. The same name we are declaring a register because I'm going to assign this parity reg inside the always block. Always at data. So this is my sensitivity list. Begin the always block. For always block, we can have a label if you want. That's optional, but that is the language allows you to do that. For this always block, I can have a label called check parity. And just like registers declared at the module level, I can declare registers at the always block level, which are local to the always block. This reg parity can be accessed if we have throughout the module. It could be one or more always block. I can access this register parity. In case of reg partial, this partial is a register declared inside the always block, so it's local to this always block. It cannot be accessed outside the always block. So partial is a register inside the always block and it is initialized to zero value, single bit value. N is an integer also local to this always block. Now this is a simple for loop. For n is equal to 0, n less than equal to 7, n equal to n plus 1. So this for loop will work 8 times, 0 to 7. Begin the for loop. Partial is equal to partial XOR with data of n. So partial initial value of partial is 0, n is equal to 0, so data is a 8-bit value. So 0 bit initially it will be 0 bit of data XOR with partial. Will again get overwritten in partial. Then the next iteration n is equal to 1. That will get XOR with partial. Again the partial value will be updated. So this for loop will work 8 times. And finally the partial value will be a single bit value. This single bit value will be then assigned to parity, which is a register, then end always block and end mode. So if you know the XOR logic truth table, XOR logic, the output is high when if it's a two input XOR gate. If two inputs are 0, 1 and 1, 0, that means odd, it is not equal. So odd number of ones will give you 1 at the output of XOR gate. 1, 1, if both inputs are 1, output will be 0. Even number of ones will give you 0 at the output of XOR gate. So we are using that concept to generate the odd parity, and that odd parity, whatever it is, 1 or 0, will be assigned to parity, and this will go out as output from this model. Okay, any questions?
Yeah, I'm still trying to understand the logic how the partial is equals to partial XOR data will give me the odd. I know the XOR, of course, will give. I know if you XOR with the data, you'll get something, but how is that gonna show me if it's odd or even? That's what I don't understand.
Okay, so let me open, let me zoom this a little bit. So partial is equal to 0 initially. Let's say data is 8-bit value. So I take 1 1 0 0 0 0 1 0. This is my data. So initially partial is equal to 0 is equal to 0 or partial and with, so 0 and with 0. Sorry, 0 XOR with 0 will give me 0 is new value of partial, right?
Yes,
0 XOR with the 0th bit of data because I'm running a for loop here.
yes, it'll give me
So again 0
yes
XOR with the next value which is 1
one.
will be giving me 1, which is a new value of partial. Then 1 XOR with the next is 0 will give me 1. 1
One, yeah.
XOR with MSB bit, your third bit, which is 0, will give me 1.
One.
1 XOR with the fourth bit, which is 0, will give me 1. 1 XOR with fifth bit, which is 0, will give me 1. 1 XOR with sixth bit, which is 1, will give me 0. And 0 XOR with the MSB bit, which is seventh bit, 1, will give me 1, equal to partial. This is the final value of partial. So partial is equal to, parity is equal to partial, which will be 1. Why 1? Because we are checking for odd parity. Now, if you see this data, there are three number of ones in the data. So odd parity is 1.
Oh, so whenever you XOR a value with an odd number, it will always give you one, and with an even, it will give you zero.
So this is the truth table of XOR gate. When both inputs are 0 0, when both inputs are same 0 0, your output is 0. When it is 0 1 and 1 0, our inputs output will be 1. So odd number of ones in the input will give you output as 1. When both inputs are 1, that means even number of ones, output will be 0. This is the XOR.
Okay, okay.
So I'm going to use this logic where odd number of ones in the input will give me 1 at the output. I'm going to use this logic here.
Yeah, I got it. I got it.
Okay, so that's how I can use this uh, XOR gate logic to generate odd parity. Now, if you want even parity, you just the final value will be, instead of partial, it will be not partial, right? So if it is, now let's say I have two outputs,
Yes.
even parity and odd parity. If odd parity output will be 1, which is partial value. Even parity output will be 0, which is reverse of partial value, because I don't have even parity in my data. It is not even number of ones. It is odd number of ones in my data at this moment. Do you agree?
Yes, sir. Yes, sir.
So that is how you can generate. If you want a even parity, just invert, just reverse or complement the final output. You will get even parity. So you can always
Okay.
generate this output at the end if you want as additional output here, if you require that. That's how parity
Okay.
generator will work for you. So you take a snapshot. If you want, you can build this. Instead of a for loop, you can use this also. So let's say, what is that data, right? So if I XOR, now partial is equal to gap data. If I do this, single line will give me this. Why? Because this is a unary reduction operator, as you remember from the earlier slides, if you remember. Unary reduction operator means it will do the same thing that we are doing in a for loop. So the zeroth bit, it will start from MSB. This MSB bit will be XORed with the next bit. Then the result will be XORed with the next bit. Then the result will be XORed with the next bit. So on and so forth till we get a single bit out. So this is called unary
Yeah, this
reduction
one
operator.
makes sense.
In that case, you don't need a for loop. This single line will give you the output.
Yes, I get this one. This one, I understand.
Unary reduction operator. That's what this will be for. Okay, so Depending on what you want to use, you can use this or that. Which one you prefer? Uh, Fine. So moving forward, now implementing adders in Verilog. As we know, there are mainly two types of adder: half adder and a full adder. I want to implement a half adder, module half adder, cout S A and B. This is my port list. Cout is single bit output port. S in this case is a 8-bit output port. Why? Because A and B inputs are 8 bits. A and B, each of them is 8 bits, so some output will be 8 bits and carry out will be single bit. Assign. Now again I can use a continuous assign statement outside the always block. Assign curly braces cout comma S braces is equal to A plus B. This will implement the adder for me in hardware, where A and B inputs will be added and it will generate two outputs, sum which is 7 bits like A and B, and cout which is a carry out single bit end module. If I want to make it a full adder, module full adder, output cout S is 7 bits, 8 bits, sorry, A is 8 bits input, B is 8 bits input, and CI carry in is another input. In this case, again I can use the assign continuous assign statement. Assign curly braces cout comma S is equal to A plus B plus CI. Since in this case I'm including carry input as a part of my adder operation, it will generate a full adder for me. This will generate a half adder for me. Okay.
Okay, so but for the full adder, because is it okay the way they declare it? Because in the brackets after full adder they did not put the uh, what do we call them?
The port list.
Like if you look at, yeah, did not
Yeah,
put the port list.
so this is another way of declaring the ports. Here we are declaring the ports, and then we are saying this port is output port, this port is input port. You can combine these two and declare a module like this, where the name of the port and the input output direction is declared in the same part. You don't have to declare it twice in this case. This is also
Okay,
allowed by the
okay,
language.
okay,
So you can do it this way or you can do it this way. The language allows you both ways.
got it.
Like, okay, so when you do hardware design, um, in after Verilog, if you remember the methodology that we have seen, after Verilog coding, we follow, or after the functional verification, we follow it with the synthesis step. Synthesis is a step which will convert your Verilog code to gate level netlist or hardware netlist. That is the first step in hardware design after Verilog is coding. When you do hardware design, you have two options. You normally do something called optimization of design, or to optimize the design. That optimization is done automatically using the synthesis software. And when you optimize the design, you have two options. You do optimization for area, or you do optimization for timing. So what that means is, you can tell the synthesis tool that if you're optimizing for area, you're telling the synthesis tool create the smallest design possible without changing the functionality, obviously. Create the smallest design possible. Or if you say optimize for timing, you're telling the synthesis tool that create the fastest design possible out of this, out of the Verilog code that you have written. You're giving the Verilog code that you have written as an input to the synthesis tool or the synthesis software. At that point, you can optimize for area or you can optimize for speed. Optimize for area means synthesis tool knows it has to implement the smallest design possible out of the Verilog code. When you say optimize for timing, synthesis tool understands that you are telling the synthesis tool generate the fastest design possible, the fastest clock speed. That means you're optimizing for timing or speed. You can choose one, you cannot choose both. It can be smaller area or better timing. You cannot normally choose both.
Okay, okay,
So as a designer, you have control over that. Obviously, there are some default options in synthesis tools. It will just go forward with the default options. But as a designer, if you want to control your design in hardware, you can do this. These are settings in synthesis. In the synthesis GUI, you can go open the GUI or the window for synthesis, and there is a setting for that. You can change that setting if required. Okay, so
Hmm.
that's how
Got
it
it.
works. So moving forward, tri-state buffers. How do we implement tri-state buffers? Tri-state buffers can be implemented in Verilog like this. First of all, tri-state buffer will look something. It normally is used, even though this example doesn't say it that way. Normally, tri-state buffers are used for bidirectional ports. So until now, you have seen a port can be declared as an input port or an output port. But you can also declare a port as an in-out port, which is a bidirectional port. In such cases, tri-state when it's an in-out port or a bidirectional port, tri-state buffers come in very handy, where you can control the direction. You tri-state one direction or you block one direction of the port temporarily till the other direction is active. So without declaring two separate ports, input port and output ports, using the same port, I can tri-state one direction. For example, always at select A or A. Now this is only the always block. We are not worried about the module declaration and other stuff. Always at select A or A. If select A is high, out gets A, else out gets Z. Z is a tri-state. Z will give a tri-state for the output. So the output side is tri-stated if select A is 0. And you can do it with other blocks and other inputs also. So the input side, now the output side is tri-stated. So the input side will work, but the output side will be tri-stated here in this case. And the same thing, now this is a behavioral way of doing it. You can use a continuous assign statement. Assign out is equal to, this is the conditional operator question mark. Assign out is equal to select A question mark A. So if select A is high, A is going to output, else Z is going to output. So try state the output if select A is 0. So you can do for in out conditions, or you can do it for, like, if you have two outputs coming or there are two inputs A and B, and if A is active, select B is out high, or like something like this. Typically speaking, they should be even resolved further, but you can solve it with a tri-state also in such cases. A input goes to out or B input goes to out. If you want, if it is connected like this and you want B input to go to output, select A should be 0. So this will be tri-stated here. And B input will go to output port. This can even be solved further, but this is one example. Even better example is if you have bidirectional ports, the same port output direction is tri-stated when the input direction is active. And the input direction is not active, the output direction of the same port can be active in that case. In such cases, tri-state buffers will be used. Any questions on this? Tri-state buffers.
No.
Parameterized design. So we know that we can use parameters in Verilog. Parameters are basically constants in Verilog. They can be defined once and they can be used multiple times. So it can be defined anywhere in the module, this parameter, and it can be used throughout the module. If you declare a parameter at the start of the module, you can use this parameter even to declare the to use for the input and output declaration purpose. In this case, just after module and the port list, I am declaring a parameter called bus width equal to 8. So in this case, this parameter called bus width can be used to declare the width of the input ports A and B. Bus width minus 1. So bus width is 8. 8 minus 1, 7 down to 0. So A and B, each of them is input port 8 bits. And I can use it throughout my design, throughout the module for that matter. It's just easier to control the design that way. So you can declare as many parameters as you want allowed in Verilog. Any questions?
No.
So till now we saw some examples of how to design combinational circuits using Verilog code, Verilog language. We saw basic gates, then we saw combinational circuits like multiplexer, encoder, decoder, priority encoders, adders, etc. So those were examples of combinational circuits. In this section, we'll see how to design sequential circuits using Verilog. Sequential circuits, as we know, the output is dependent on input and there is some memory element that is associated with a sequential circuit. So it will remember the last value of the output unless the input changes and in such a way that the output changes. Examples of sequential circuits or sequential logic circuits are D flip-flops or D latches, registers, normal register, shift register, counter. We will look at a pipeline example, how to design a pipeline logic, and obviously FSMs, finite state machines, how to design them. So a simple D flip-flop can be implemented in hardware using the simple Verilog line. Always at passage clock, Q gets T. Passage clock means positive edge of the clock. So a clock, as you know, is a free running clock. So every clock period, once it will have a positive edge, once it will have a negative edge. Your D flip-flop normally is a edge-triggered flip-flop which will work on the passage or the neg edge of the clock. Very usually it is a positive edge of the clock. So on every positive edge of the clock, the always block is triggered. On that positive edge, whatever the D value goes to output Q. This is a classical definition of a D flip-flop. So in hardware, in netlist, a D flip-flop will be implemented. In this case, passage, but you can also use neg edge. Now this is examples of synchronous clear and asynchronous clear. In Now in this case, synchronous clear means the clear is also synchronous with respect to clock, because clock is my common signal. Module D flip flop, Q comma D, Q D clock and clear. This is my port list. Q is the output port single bit. D clock and clear are input port single bit. There is a reg called Q with the same name as output because I'm going to assign it inside the always block. Always at passage clock, begin. So only the positive edge of clock will trigger the always block. So this is a synchronous logic. Synchronous with respect to clock. Begin the always block. If clear is equal to high is equal to one, or if clear is high, output is zero. One tick binary zero. Else output gets D. End always block end module. So clear, all this logic inside the always block is working with respect to positive edge of clock. Clear is also working with respect to positive edge of clock. Hence it is called synchronous clear. If it has to be asynchronous clear, this always block will be replaced by this always block. Always at passage clock or passage clear. Positive edge of clock or positive edge of clear. Anything can trigger the always block. Begin the always block. If clear, Q gets 0, else Q gets T. In this case, clear is not always dependent on clock. It may happen that the positive edge of clear is coming at a time when there is no positive edge of clock. But still, that positive edge of clear will trigger the always block. At that point, clear is equal to 1, output will be 0, else output will be D. In this case, clear is not dependent on clock, hence it is asynchronous clear. Okay.
Yes, I get it.
So anything with respect to clock, everything is synchronous. Anytime it is not dependent only on clock, it can be asynchronous logic. And wherever possible, you should avoid developing asynchronous logic. You should use synchronous everywhere. Even clear, which is a reset signal, has to be synchronous wherever possible. This is a register. In this case, it's an 8-bit register with set and reset. for set and clear. Clear bar, set bar. So in this case, clear and reset logic is active low. Module register QD clock clear bar set bar. This is my port list. Q is the output port 8 bits wide. D is the input port 8 bits wide. Clock clear bar set bar indeed are all of them. Each of them is the input single bit. There is a reg called Q 8 bits. Why? Because I'm going to assign this reg Q inside the always block or output Q inside the always block. Always at passage clock or negate clear bar or negate set bar. Begin the always block. This is my sensitivity list. If clear bar is equal to 1 tick B 0. Clear bar is 0 means clear is active. Output is cleared. Q gets 8 tick binary, 8 bit binary 0 0 0 0 0 0 0 0 means output is cleared when clear bar is 0 or clear is else if set bar is equal to 0. Set bar is equal to 0 means set is active. Set is active means output gets all ones. Q gets 8 tick binary 1 1 1 1 1 1 1. Else means clear is not active, set is not active. Output Q gets input D value, whatever that is. D is 8 bits, Q is 8 bits. And the always block and end now. So this will implement Q and D both are 8 bits. So this will implement the 8-bit register in hardware which is synchronous. Now tell me whether this is clear is synchronous and whether set is synchronous.
Okay. Yeah, though something is happening to your microphone, but I can hear
Hello.
you.
Can you hear me now?
Yeah, I can hear you.
Okay. So my question was whether set and clear whether they are synchronous in this example.
Uh, no, because whenever you know they are in the always block, they can also trigger the the setting of the queue or reset.
Okay, that's why they are asynchronous.
Yes.
So what change can you make there to make them synchronous?
So I just remove them from the always I mean from the sensitivity list,
So
and
your
I
new
think it will be
sensitivity
okay.
list will be what in that case?
Will be always at positive clock edge only,
Okay, that will
and
make
remove this.
right. So that will make the entire logic inside the always block synchronous with respect to clock.
I believe so. Yes.
Yes. So okay, so that's how a 8-bit register with synchronous set and clear can be achieved. And this is active low. So if you want to develop a register which is active with active high clear and active high set, what is the change that you would make in this design?
Uh, well, so this is you said this is active low, so
Yes.
we're gonna remove the what do we call it the bar sign from the negative edge clear and negative set. So we remove the bar sign, and
Mm.
I think it will change back to positive.
You don't have to make any change. You just remove the bar and that will do it. Is is that how it will work?
That's Yeah, that's what I'm saying.
So how do you define an active low signal and an active high signal? Do you remember from digital logic section? How if you define some signal, how do you say it's active low or active high? No. Okay, so active high means whenever the signal value is 1, we do something, we take some action. That's how active high signal is defined. On the other hand, active low signal is defined that whenever the signal value is 0, we take some action. That's how active low signal is defined. In this case, as you can see here, if clear bar is 0, then we are taking some action, which is resetting the output. If set bar is
Yes.
0, we are taking some action, which is setting the output. Now, if I want to change it to active, this is active low right now. If I want to
Yeah.
make it active high, first thing is just the this thing, that I will remove the clear bar from clear, underscore from this, and underscore from this. So this will be clear and set. But that is just the cosmetic change. The coding change I have to do is, in that case, if clear is equal to 1 tick B1, then Q gets 0. Else if set is equal to 1 tick B1, Q gets 1. Because in that case, active high means clear has to be 1. Only then output will be clear. Set has to be 1. Only then output will be set. Else Q gets D.
Oh, okay, okay. I think I missed that.
So removing a bar underscore is correct, but that's just a cosmetic part of it. Active high means this has to be 1. Then that signal is high, is active, means reset the output. Set equal to 1 means this signal is active, then set the output. And that goes for any signal that is active high or active low in your design.
Okay, okay, I got it.
Okay, so what time is it? Okay, so I think we'll stop here today and we'll continue next with the rest of the stuff from in next lecture.